turns out that there are some kinds of equations that kind of are in a category of their own. Basically, they aren't functions. And when an equation is not a function, it means that it's not a nice, neat y equals. I'm not talking about just y equals mx plus b. I mean, every problem on your quiz was y equals something. We'll get to this problem, but I just want you to see what I'm talking about. There are equations that aren't y equals. Okay, now when you encounter an equation like that, you can still do its derivative because it still has slope. Even though it would be hard to graph this and we might need like a fancy computer, this is still a graph. Now, it's not a function. It's not like just a parabola, but it's still a graph. So it still has slope. So it still has a derivative. So don't give it a hard time. Let's talk about how to do the derivative implicitly. Implicitly means that it's not explicitly y equals. Okay, and it also means that we kind of have to think a little bit. I'll be careful how I say it. I mean, it is a little differently, but I also want you to realize that we're still thinking the same way. And so to do that, I want you to think with me about the derivative of x cubed. You say the derivative of x cubed, I mean, isn't that just 3x squared? Yes, but I want you to think about it with me using the chain rule. Okay, now the derivative of x cubed, if I'm using the chain rule, would be kind of like forcing us to think about x as being on the inside and 3 on the outside. Now, let's do the chain rule. By the way, on the quiz, overall, your guys are at a great spot. In other words, you understand the chain rule, so I hope you understand when I write down a 3, when I leave the inside alone, and when I also finish the derivative. So now that's part of the chain rule, right? That's the outside with the inside left alone. What comes next? What's the derivative of the inside? What am I going to chain onto the end of this? 1. Now, just so you know, that's why we usually don't think this way, because you're always going to get a 1. The derivative of the inside is going to be 1. Unless the inside is a different variable. Okay, now we're going to use the chain rule, but we're not going to get 1. We're not going to get 1 for the derivative of the inside. So what are we going to get? Okay, well, let's use the chain rule. That's good news. That's what we always do. You bring the outside, you do the derivative of the outside, you leave the inside alone, you finish the derivative of the outside. Okay, here's where things change up a little bit. What's the derivative of y? Now, don't say 1, because at least like 30 seconds ago I said it's not going to be 1. But here's why. Okay, the derivative of y is like asking what's the derivative of like the whole equation. Do you understand that the derivative of the whole equation has always been described as dy dx? What's dy dx? Why is that chained onto the end of this expression? Dy dx is the derivative of y. It's the unknown. It's like what we're trying to find. But see, the derivative of x is like a diagonal line, you know, like a line that has a slope of 1. Okay, so when I talk about the derivative of x, a line that has a slope of 1, I'm allowed to write down the number 1. But when I talk about the derivative of y, I don't know what y is. Y might be a graph that goes like this, or goes like this, or I'm not a good dancer, but it's some kind of graph. The derivative of y is the unknown. It's dy dx. Okay, now, even if you're a little bit like, I think I understand, you'll see it again and again. And basically, it's how we navigate an implicit problem. So when we have implicit differentiation, what we're going to end up doing is the derivative of y, and you'll find out it's kind of like embedded in the problem. You can write that down if you want, or you can just read that. Same thing, you can write it down or you can just read it, but the derivative of y, just kind of so you get the gist, it's always dy dx, even if you're still a little fuzzy on y, but it's always dy dx. And so that's why we end up using like a chain rule. That's why we end up using like a chain rule to do the derivative of something like, for example, y cubed. Again, just to give it a little emphasis, I'd like to do a problem with you where y is like embedded in the equation. In other words, it is not explicitly y equals. And what you're going to find out is that whenever we get to the letter y, as the letter y kind of shows up in the problem, we have to think a little bit, we have to think about how to apply this chain rule. And you're going to find out that we always apply it the same way, okay? Because we always end up with this inside derivative, again known as dy dx. X cubed plus y to the 6 equals 24x. Different equation. Wouldn't have seen it on the quiz. Okay, but the good news is we still do the derivative. Okay, we still do the derivative of x cubed. Now, just to make sure you guys don't overthink this, anytime you're doing the derivative of an x, you can just think normal. You can think normally. Okay, so I don't need to put an extra like chain rule in this because it's going to be 3x squared times 1 every time. However, as soon as you get to the derivative of a y, you must think chain rule. Now, those parentheses might help you to do that. But just so you understand, it's still going to be 6y to the 5th. Like that's how you do the derivative of an exponent. Okay, here's the one part that's different. And we'll get it. But I also have to think about the derivative of the inside. Like I left the inside alone when I wrote down the letter y. So I left it alone. But now I have to do the derivative of the inside. What's the derivative of y? dy dx. We chain on, we multiply on a dy dx. Hey, the derivative of 24x, good news, it's 24. Let's finish this, because if you're kind of like, what's this dy dx? Well, it's what I'm trying to solve for. Okay, in about 2 steps, we're going to solve for dy dx, which, by the way, has been your goal for every problem in the last many weeks. So it's kind of like I have a little equation up here that I just need to solve. You know, like move stuff away. So I subtract 3x squared. So we subtract 3x squared. (24) minus 3x squared. And then you divide. You divide by the 6y to the 5th. You divide. And look at the kind of answer that you get. It's different, but it's a derivative. It's different, but it's a derivative. It's 24 minus 3x squared all over 6y to the 5th. Now, the reason it's a little different is because in this answer is a y. But that's because in my original problem, I had a y that was kind of embedded. So now I end up with a y in my answer. But it's still a formula. It's still a formula for slope. Okay, and we'll talk more about how to use this method once you guys come back. we opened up another can, didn't we? Implicit. Okay, now implicit is needed when you have these equations that, well, they're really not functions, but you want to understand they're still equations. So they still have a derivative, and our goal is to find it. I want to do one more that sort of fits into this little intro sort of category. All right, so it's different. It's implicit. Implicit means that it's not explicit. What's explicit? Y equals. Okay, but this isn't y equals. It's actually x squared equals. We can still do the derivative. I want to make sure you get the idea that we're actually doing what we've learned all along. That is the derivative of both sides. You always do the derivative of both sides. It just so happens that the derivative of this side is going to require a quotient rule. A quotient rule. Now, if I could just say nicely, that's what some of you missed on the quiz, but it was the product rule. And I've told you, and we're going to keep learning, but the product rule, it kind of can get a little hidden. It can get a little, we can miss it, but quotient rules usually, they're a little hard to miss because they're fractions. Okay, so we're going to do the derivative of the quotient. It's ho d high. Now ho would be the bottom, d high would be the derivative of the top. Take a look at that. I'm not changing the rules. The derivative of the top is 2, and the bottom is y. Now it's ho d high minus high, which would be the top, d ho, which would be the derivative of the bottom. Aha, the derivative of the bottom. The derivative of y is dy dx. What you're going to learn is you always get a dy dx kind of like inserted into the answer. Okay, you always get a dy dx kind of inserted, and sometimes you'll get more than one. Here we kind of get that dy dx as part of the derivative of the top. Excuse me, the derivative of the bottom. Okay, don't forget the ho-ho. And don't forget to do the derivative of the other side. Okay, now, you've always done the derivative of both sides. It's just that the one side was always y equals. So it was really easy to do the derivative of y equals. It's dy dx. Now we have two sides that we kind of have to use rules. But you always do both sides. Now, you got to solve for that. Okay, it's algebra time. You got to solve for that. You got to feel like you're going to move things around. And, do some inverse operations. Get y squared over here. Let's see. Multiply both sides by y squared. 2xy squared. And then one more subtraction and one more division. Okay, we'll subtract 2y. And we'll divide by negative 2x, right? You'll divide by negative 2x. These are the way these answers can look. They basically can be a mixture of x's and y's. So I subtract 2y, I divide by negative 2x, and we get dy dx. Even though I'm just going to recopy it, we get dy dx equaling 2xy squared minus 2y all over negative 2x. What are you seeing? What do you want to ask about kind of as an intro here? Because we're going to do some more. We're going to keep going, but anything with all the x's and y's? All right. Well, we're going to kind of turn up the difficulty meter a few notches. X squared times y plus 3xy cubed equals 5. All right, now maybe some things grab your attention, like if you notice that there's a couple different y's. Yeah, there's y in a few places. That doesn't matter. It just kind of makes it more implicit. What I really want you to see, and here's the thing, it's not new. I want you to see that product. It's actually the same thing over here. I want you to see that product. I just know that this is maybe one of the main things as we go through this chapter that students have trouble seeing, doing. It's when there's a product. Now you're like, how do I know to put the dot right there? It's kind of separating the two functions. The reason I put the dot here is because this 3 is a coefficient. And I'm telling you, if you just let numbers act as coefficients, it's a lot easier. So I always want to put my product between the two variables, between the functions. We're going to do the product rule twice. Okay, it's going to be good if you think about it. Yes, I'm going to write it down, but first is x squared, derivative of the second. Right away, the derivative of the second is dy dx. First derivative of second plus second derivative of the first. So we get a y and a 2x. We get a y and a 2x. And that's one product rule. Same thing. Maybe you want to think about it. I'll pause a little more here. You're just going to do a first derivative of second and then a second derivative of the first. Love to see you do the derivative of y cubed correctly. The derivative of y cubed. Before you go too far, again, the derivative of y cubed. Now, that would be the first derivative of the second. I'm talking about the derivative of the second right now. This is like the new idea for this section. Okay, the derivative of y cubed. It's actually right up here, but you have to think. You have to think inside, outside. Whenever you have a y, you think derivative of the outside with the inside left alone. Now, that's like a 3y squared. Okay, so you get a 3y squared, and then you do the derivative of the inside, the derivative of y. What happens is you basically get a dy dx tacked on. You get a dy dx tacked on to your derivative. But it's because of the chain rule. Okay, we're doing the chain rule on a y cubed. All right, if you have to change it, change it. I'm glad you tried it. That's first derivative of second plus second derivative of the first. That would be y cubed copied down, and then the derivative of the first is just 3. X's and Y's, oh my. X's and Y's, oh my, everywhere. But here's some good news. The derivative of 5, well, it's supposed to be good news. The derivative of 5 is 0. I saw some of you do that, which is good. Be careful, though. I've seen people like keep the 5, and then as you go through the rest of the answer, you get this 5 that's not supposed to be there. But there is supposed to be a 0, which sometimes people don't like zeros, but again, it's supposed to be there. Okay. X's and Y's, oh my. I'm putting boxes around the two sort of terms that have dy dx. Are you catching my drift? Both of those have dy dx. So I kind of want to hold on to them. But these two things, get them out. These two things, just move them to the other side. Okay? So we're going to end up on the other side of the equation with a negative 2xy and a negative 3y cubed. Because both of those get subtracted to the other side. Are you guys all right so far? We've got some more algebra. It's algebra that you've done. You just got to keep track of it all. Both of these boxes have a dx dy, a dy dx. Okay? Now, because it repeats itself, and I know I've said it to my students in other years, some of you have heard this, but if this is a repeat, the only way to make it become 1 is to factor. Make sure you catch this. I need 1 dy dx. The only way to get 1 is to factor. Okay, so we factor out a dy dx. It's like a GCF kind of factoring. Okay, I'm left with just x squared, and then I'm left with all this 3x, 3y squared stuff, but those two 3's should become a 9xy squared. And of course, all of a sudden, it looks a heck of a lot nicer because all you got to do is divide. All you got to do is divide, and you'll have your derivative. Just giving a little pause time here, let you catch your breath. My calculus teacher in college, he would write with his one hand and he would erase with his other hand. So as he was writing, he was erasing the last thing. Not exactly, but he kind of moved pretty quickly. I'm giving you guys a chance to just think. He was actually a lefty, so it was actually really hard to write and erase. Here's something, just so you know, when you're checking your work, as you guys look in the solution manual, it's part of this class. Sometimes things like this, like a double negative, will get factored out, and you have to be aware that it's still there. You know, the double negative gets factored out and leaves us with a positive version, but it's still the same thing. But those are things that when you're checking your work, don't be like kind of lazy and just change it. Realize it's the same. This answer's fine. Maybe this answer's a little bit better, but I'm more interested that you realize that it's the same. Let's see. You try. You see if you can maybe take this one from start to finish. So we've got 2y equals x squared plus the sine of y. Didn't do one with the trig function yet because I'm kind of curious if you can adapt. Can you adapt to that trig function? All right. Just wanted to give people a chance to think about 2y. Right? It's something that everybody can get. Sometimes it just takes some thinking. Now, a lot of you got it correct, and just to be clear, that the derivative of this can be thought of like, well, there's a coefficient. So I'm telling you, every time there's a coefficient, the derivative is, it just comes along to the derivative. And then you're like staring at this y, and the derivative of y, okay? The derivative of y is dy dx. But the reason is because it's to the first power. If you think of it as to the first power, then you could, if you ever get stuck, you could think about doing a little chain rule. In other words, bring down the 1, leave the inside alone. Some of you skip that, and it's fine, but leave the inside alone. You now get a new exponent of 0. Okay, and of course, an exponent of 0 just cancels out. It becomes a number 1. So are you making a connection? Anytime you have a single y, you're just going to end up with a dy. But if you have more y, like y cubed, then you're going to get a regular y and a dy. So it depends on how much, I should have pointed right here. It depends on how much you start with. If you start with y to the first power, you just get a dy. But if you start with more y, you get regular y and dy. Okay, it's this one that's usually tricky for students. I like that you guys tried it, and a lot of you got it. Nice job with the trig function. Derivative of the outside is cosine. Leave the inside alone. Derivative of the inside. Little chain rule there. All right, so did you guys solve this correctly? I think you did. I didn't really have the answer memorized, but a lot of people take this dy dx cosine and bring it over here. If I bring it over, I'm going to factor out dy dx and now have a subtraction of cosine. So I bring that cosine over, but it's now subtracted, and that's what gets divided. You divide by the quantity 2 minus cosine of y. All right. So we get dy dx equals 2x over 2 minus cosine. All right, there's a lot that you guys saw today. I appreciate your attention. We'll actually finish tomorrow. Okay, we'll finish tomorrow.